I've been doing my own kinds of experiments. I got lasers, right? I got a green and a red laser, and I did my own little bits of experiments. And a part of me is starting to wonder if I'm crazy and I'm the one being foolish for being so sure of my ideas and my ways, or if everyone else is wrong. And I'm pretty convinced that light is not really reacting. I did a little research, and by a little I do mean a little. I didn't go crazy in depth with this, but a quick search of where the idea that light is a wave came from told me that it originates from basically the original double slit experiment. And I don't mean the one shooting single particles and getting a diffraction pattern. I'm talking about the original just shooting light through two slits and getting a diffraction pattern. And at the time, right, they decided what was written down in this response, this was just a quick Google search, so it wasn't necessarily what they wrote in their paper, but the summarized thing was that wavelength and the proof of light comes from this two slit experiment because it was the only possible explanation for why this diffraction pattern was there. Light must behave like a wave because there's no other way we would get this diffraction pattern, because how else do we get these diffraction patterns? Well, we see when you put two slits in a wave, and send a wave of water through these two slits, you also get this diffraction pattern. It's the same thing. It must be the same thing. And I want to point out one of the most important parts of science. Correlation is not causation. And so just because something looks like something and it seems like it should be something does not mean it is. And I want to emphasize that because it's one of the cornerstones of everything now. A lot of our physics is based off of wavelengths and this light being a wave. And Einstein showed up and said, light is not a wave, but a particle with the photoelectric effect. And everyone said, oh, that's really interesting. So light's not just a wave, but it's also a particle. So it has a particle-wave duality. We held on to this wave idea, even though we were given evidence to prove it the contrary. And I can understand these people in the past, the scientists that first discovered this, thinking it must be a wave, because Einstein's theory of relativity and the idea of light being a particle didn't exist, right? There was no relativity. There was no Einstein's theory of gravity. There was none of this stuff to give a possible other explanation. But when Einstein came up with these theories and we found them to be correct, we should have gone back and done a better look at things. Because the more and more I look, the more evidence I find that light is not really a wave. Light is just a particle. And it may have some wave-like features because what is happening is that a material is radiating out bands, basically, of photons at a time. So that could be why we see this wave pattern here. But the reality is that light doesn't really behave like a wave so much as like a particle. I see particle behavior a lot more common than wave behavior. And if you disagree, now I want to ask you, when you do the double slit experiment, those waves go in every direction, right? They go in every direction. And, then we can say, oh, well, the light's going in every direction. But not really. Not really. Because if it was, where do shadows form from? Why do we have shadows? And why do the shadows get bigger when you get closer and not smaller? Because if light was working like a wave, it should be... I don't know if that's a good argument. I'm not even going to continue that thought. The more I think about it, I feel like I'm going to... the problem that I've run into, and why I think, am I crazy? Am I wrong here? Is because we have created our model, right? We have created an explanation and come up with a theory that works effectively. It works really well. And so it's hard for me to show proof against it without someone coming up with an explanation to the contrary. And I think that I have found proof, but I also don't know everything. And so there's a chance that what I think is definitive proof is actually been explained in another way that makes some logical sense. Now, I've seen arguments that make absolutely no sense, such as the theory that every photon, every part of the wave of light is creating a new wave of light that builds off of it as it goes. That doesn't make any sense because we shouldn't have shadows at all if that was the case. And, when I think about it, if that's the case, I think that light should actually get brighter as it goes farther away. An initial thought looking at it, because the points where, if you have all these points, there's these convergence points that should have twice as much light on the node, these nodes where these... I'm going to stop with that thought. Continuing on. But, what I'm trying to say is that we know these things exist. So why... We know that gravitational lensing exists, right? So why are we ignoring it? Why are we ignoring it so much? I feel like gravitational lensing hasn't been taken seriously enough. And my definitive... a point to make towards definitive proof that what's happening is not interference, to say, but is really just gravitational lensing and a focusing of light, is that when we do the two-slit experiment with a laser, we notice the diffraction pattern. And if you only have one slit, this diffraction pattern goes away, right? But that's not true. If you take your slit, your single slit, and you tighten it, right? You make it a very, very thin slit, that diffraction pattern comes back. And my question to potentially someone who's more knowledgeable than me is, why? What is your explanation in a wave sense that makes sense? Because I looked up, I was like, well, maybe since there's this slit, maybe the light, some of the light is going straight through, some light is hitting the sides of the slit and is getting refracted off, right? Maybe that's what's happening. That's my only possible explanation. But I don't think that's it. Because if it were, I think and this is again where I come to, am I being crazy? If it were the case, then when we look at a wave of water going through a slit, right? I did the ripple simulator. I looked up ripple simulator because I didn't know how else to really test this. I looked up ripple simulator online, or wave simulator, and ripple simulator came up, and I brought it up, and it's just this website where it's simulating a wave being generated, a single wave being generated, like in basically like a puddle or something, but it's like a square box. And you can draw a line, or you can make a slit and have like a wall, so that the only place where the wave gets through is through this slit. And so I made it, and now it does bounce off walls in this simulation. Is it perfect? Maybe not, right? So this is why I don't know for certain. But when I created this ripple simulator simulation, and I put a single slit in, right? What I noticed was a single wave coming out. You do not get the diffraction pattern. And I don't know if maybe I just didn't test it rigorously enough, but I don't think you do get that diffraction pattern coming out, even if you make the slit really tiny for the wave, for like a wave of water. I think you still end up with a single wave coming out on the other side. And maybe I'm wrong, and I would like for someone to show me proof of otherwise, because as of right now, I'm very divided on this, because a part of me is like, I know I'm right. I know I'm right. But the other part of me is like, right? So you still get this diffraction pattern. Where is this diffraction pattern coming from if it's not from the light interfering? My argument is that of gravitational lensing. And you may say, what? Sam, how could it possibly be lensing? You know, I get this diffraction pattern with a single sheet of paper. How could it possibly be lensing? And I think you need to think about just how tiny a photon is compared to this sheet of paper. And that really is the key. And I also think you need to think about how massive an atom is compared to a photon. And that really is the key. Because when you have the walls far away, you don't get this gravity. When you have a wide slit, you don't get this effect. It's not until you really squeeze them together that you start to see this happening. And that's because as these photons are flying through, they're closer and closer to the mass of these walls. And the photons that are right next to the wall, well, they get bent the most. And then the ones that are, kind of in a little bit, they get bent a little less. And then the ones that are farther in, they get bent a little less. And then, you make it into the middle, and they just go straight through. And the majority of these laser photons coming from the laser go straight through, right? And then you get this diffraction patterns on the sides. And the reason why you get this diffraction pattern, and it seems like it's light, no light, light, no light, light, no light, is because these photons are getting bent, right? They're getting lensed by the gravity of the sheet of paper, which again seems ridiculous, but again, I think we're underestimating the significance of gravitational lensing. I don't think I can understate that enough. Gravitational lensing is not a stellar phenomenon. It's everywhere. Because gravity is everywhere. But continuing on, we know that gravitational lensing exists. And what we notice, like if you bring the slit of the laser closer and closer to the point where it's connecting, that diffraction pattern starts to combine and fall away. And the reason for that is because the light needs to travel a distance, right? Because once it's been bent, it stays in that new straight path. But once it's been bent, right, when they first get bent, they're like this. And it's not until you go farther and farther away that they start to diverge. And you get this seeming gap in between, but it's because light at a certain distance, right, it's a deciding factor. Light that is this far away gets bent this much. Light that's this far away gets bent this much. And now this isn't even part of my talk, but it is a point that I actually do need to bring up. And the question is where's that dividing line? Well, there's two possible options here. One, gravity is quantized, and at certain distances, there is that definitive point. Or two, it's just the fact of how energetic the photons are, and any photon that is this distance away, because light is quantized, that they just aren't affected anymore. And they're far enough away that the effect is not there. So it's one of those two things. And honestly, which one, I'm not certain. It's probably more likely the light, but again, that gets back to gravity might be quantized on that level. So an interesting point to make is, we're looking for this quantized gravity. Where is it? It might be right in front of our face. I don't actually know, though. That is complete off-the-cuff postulation. But if I'm right about this gravitational lensing causing this diffraction pattern, something to look into. Anyway, continuing on. As the light travels farther away, we start to notice this point where there is light and there isn't. And it's not that the light is interfering and, it cancels out in these points. No. Because if you really think about it, we know light is a particle. We know light's a particle. So when two photons hit each other that are the same photon, why would they cancel each other? They're not opposites. They're the same thing. Right? If they're traveling in the same direction, at the same energy, why would they cancel each other out? I don't know. I guess you could listen. I understand, but I disagree. I don't think that light is necessarily interfering with itself. I think it's gravitational lensing. Another argument that I have is that when you have, say I take my water bottle, this water bottle here, and I have some photos, maybe I'll put them up to show my points, I probably will, I'll add them in on this video, but I shine the laser at this, on the side of this, right? What I notice is if I'm shining the laser here, on this back side, there's no light. I don't see the light on this side. I only see the laser here. But I do see enough of the laser is pushed off to the side that it goes straight out and hits the wall still. But what else do I notice? Light is getting bent out pretty significantly out to this side of the water bottle. But I also see some light in a line for a shorter distance, a much shorter distance compared to how much it stretches over here, towards the inside of the water bottle, as if the light is shining through the water bottle itself, but it's not. So how is light that is completely blocked here getting stretched out, right, on the other side of this? what is causing the laser light to get slightly stretched out on the other side of this? And this is very important because it couldn't, a laser, if you move the laser just over a little bit, it's a single dot. It's a single dot. It's not spreading out. It's not stretching. So there's something is happening on this water bottle that is causing the light to be, reflected a little bit or diffracted a little bit to the inside of the bottle. Seemingly behind the bottle, the light is bending. And the question you need to ask yourself is, where is that light coming from? Because if gravitational lensing is not the case, and we know that lasers are straight, lasers are a straight line, right? Why once I introduce the bottle, do we get light on this side? Take the bottle away, straight line. Bring the bottle in, right on the edge, right? Right on the edge here. If we put it too close to the edge, if we put it too far inside, then you don't get this effect. But if we put it just on the edge, then you start to see light bending in. And I'll show you the photos. If not gravitational lensing, how does that happen? Where is that coming from? Where is that light coming from? And if that's gravitational lensing, then why can't anything else be gravitational lensing? And the reason why the line is solid, because I know it might get brought up, is because there is a constant surface for the light to be bending across. And there's nothing on this side to deflect, to interfere with it as well. I really feel crazy right now because, to my knowledge, no one sees light this way. And I don't understand why. We know these are real things. We know these are real phenomena. We know that we have all of this proof of them being true. So why do we not see that this diffraction pattern that is formed has nothing to do with the wave, with light being wave-like? And this means a lot because everything, quantum mechanics is based off of this wave, these fields creating waves. And this wave idea is based off of light being a wave, which is found from this diffraction pattern. And I don't know how we decided out these wavelengths. From my understanding, it comes from this double slit experiment and trying with different lights. But I don't think we need wavelength. I don't think light needs to be a wave for anything to be explained. And I could be wrong about that. But from my understanding, it doesn't make any sense. Because here's the thing. If light is a wave, then lasers aren't possible. They're not. Why are they not possible? Because light is a wave, and a wave expands out in every direction. Right? So even if you columnize the wavelengths, right? Even if you focus the wavelengths, right? Because the explanation that I saw for how lasers work is that they create photons, and these photons bounce back and forth in a mirror to concentrate themselves, and then a little bit seeps through on the one mirror, and that shoots out a columnized beam of light, right? So we have our laser here, And the light is bouncing back and forth inside of here, and then comes out this side in a straight line, right? And we say all of these are perfectly in sync, right? The waves just float out like this. Here's the thing. This is a 2D wave. We live in a 3D universe. Light waves do not look like this. The light wave that would come out of there would not just go like this out. They don't look like this. They look like this. They expand out in every direction, right? That's how light would work. And if not, and if they do look like this, if you approximate these squiggly lines, you know what you get? A straight line. You get a straight line because this high curve balances out with this low curve. And when you approximate across this whole thing, you have a straight line. So there's no wave. It's a straight line. So if this is how a wave works, it's a straight line. And if it's not this, and it's expanding out in every direction, you can't possibly get such a concentrated beam because the light is going out in every direction. So by the time the light goes from here to there, it should have expanded in every direction, equally. But it doesn't. And you can shine a laser beam for crazy distances. And none of the light goes anywhere. And the light barely scatters. And, maybe I'm wrong. Maybe I'm a complete idiot. But that doesn't make any sense. Because as soon as the light goes through the beam, it's expanding out in every direction. Right? And with every other light, that's exactly what happens. What we're shooting out here is a beam of particles. A beam of particles, not a wave. And we call it a beam of particles when we're doing the double slit experiment. When we're shooting a beam of particles, it's a beam of particles. A laser is a beam of particles. It is not a wave of light. I digress. I don't understand why we're holding on to this theory that there is many things that prove it wrong. And I don't understand why it's so laughable to think it could be wrong. Isn't the point of science to improve? I'm literally making nothing new up. I am just taking what has already been discovered, been experimentally proven to be true, and pointing it towards something that to me is flawed. It doesn't work. We've made it work. We've made it work. I don't think it's true. Because I didn't do a lot of research into this, but if the way we discovered wavelengths is by measuring the diffraction of light in like this two-slit experiment, and we then use that to approximate a frequency, and then we use that frequency to get an energy, and then we compare that energy to other different forms of light, and then we approximated their wavelengths based off of that because we can't actually see those diffraction patterns, then the whole thing is built the whole thing's a house of cards. Because if we pull out this diffraction pattern being caused because of light's a wave, that whole thing falls apart. And again, now we go back to the two-slit experiment from, shooting a single particle through. We no longer have this weird mystical superposition, a single particle interacts with itself shenanigans. The whole mystery is gone in an instant. Because if a particle goes through two slits, right? And here's how we solve this, right? Do the mystical 2-slit experiment through a single slit that's really thin, right? And if you can do that and still get a diffraction pattern, a single particle shot through a very, very thin slit, I'm curious what happens. Because if we still get the diffraction pattern with a single particle flying through, right? And then we measure it, and then all of a sudden they're all hitting smack dab on, right? What's happening here is when you measure the particle, you give it energy, and this goes, right? You give it energy, and if you give it energy, as you measure it to figure out which slit it went through, then it has enough energy to not be affected by the gravitational lensing, right? And they all of a sudden aren't affected by the gravitational lensing anymore because they have more energy than they initially would have. But if you take that away, all of a sudden you get a diffraction pattern again. And it's not the observation, it's the adding of energy into this slit experiment. But if we have these 2 slits shooting through the wall, right? And on the back side, say over here, right? We're getting this weird, it's not the best drawing, but we're shooting a single particle through, we're getting this diffraction pattern. That's because we don't know where every particle is, right? We don't know where every particle is. That's why we have to measure it to find out which slit it goes through. So some particles might go straight through the slit, through the wide open gap. But every once in a while, we have particles that go close to one of the edges. And when it goes close to one of the edges, it gets bent by the gravitational lensing. And if that's not the case, how about we try and shoot the particle through at varying speeds, with varying energy, right? And see what happens. If we still get this crazy diffraction pattern, right, when we shoot it at, 0.25 the energy, and then at 100%, right? If those are if we get the same exact results with no difference, right? Because if it is a diffraction pattern, and it is this mystical woo-woo stuff, right, of quantum superposition, we should get the same exact thing, right? We should get the same exact thing, right? But if we shoot it through, and we're getting a diffraction pattern at 100% energy, or if we shoot it through at 100% energy, and we don't get a diffraction pattern, right? But if we shoot it at 25%, we start to get a diffraction pattern. Shouldn't that tell you something? I don't know how many experiments have been done with this, but personally, if I was a scientist that had the equipment to be doing this test, I would have done everything under the moon. I would have varied this in so many ways because believing that a single particle is interacting with itself doesn't make any freaking sense. And gravitational lensing makes a whole lot more sense to me than whatever this craziness we've come up with is. And I'm saying, the thing is like the result and the location is still not necessarily predictable, right? It's still kind of got this quantum sense to it. So I'm not saying everything is trash, but I'm saying some of the fundamental building blocks of the theory are flawed. They're flawed. And we can't fit gravity into our theory because we ignored it. Because we explained it away with other stuff. It's already there. That's another thing. I think gravity is already in our formula. It's already accounted for. We just don't know it because we called it something else. That is why trying to add it in, it just doesn't seem to work, but everything is predicted so accurately. Because it's already there. Or at least a part of it is. I think that when you look at dark energy and the behavior of dark energy, and we look at gravity and what gravity is, I strongly believe that dark energy is basically the medium that we are in, right? And we are consuming this energy in order to, well, not we, I mean, matter in general is consuming this energy that is all around us. And this dark energy has been evenly distributed throughout the universe. But wherever there is mass, mass is consuming this energy. And what happens when you consume that energy? All of a sudden, it's not equal there anymore. Well, we gotta fix that. We know that hot flows to cold, right? High energy flows to low energy. So if mass is consuming the energy, mass is creating a point of low energy in order to sustain itself, right? Well, what is that energy going to do? It's going to flow to fill that space from every direction. Every direction, the high energy is going to flow towards the low energy. And the less and less energy at a point, the stronger the flow is going to be. If you put a very hot thing and a very cold thing next to each other, the reaction is going to be a lot stronger than if there's two things about the same temperature, right? And so, what do we see? Larger, more massive objects have stronger gravity. Gravity is basically a current. It's a flow. It's dark energy flowing in. And we see this happen, the Casimir effect. The Casimir effect. We say, oh, well, it's the dark energy. There's higher pressure outside, right, because of these different wavelengths. Screw the wavelengths, guys! You're right for the wrong reasons. We're so caught up in these waves. We're so caught up in these quantum waves, and we've got this string theory with we need like all these different dimensions. We don't have those dimensions. We don't have those dimensions. They're not here. What are we doing? I feel like I'm crazy because I'm looking at these people that are so smart, and all I see is sorry, but stupidity. And that's why I'm like, am I crazy? Am I wrong to be so confident that I'm right? And I don't know. But anyway, getting back to what I'm saying, is that the energy is flowing in. And so what happens when you try and throw a massive object towards this fluid that we're surrounded by? Well, it gets affected by this flow and it gets pushed back, right? And so when you have something that is capable of creating a singularity, and I also think this is another reason, in quantum mechanics, right, let's say in the standard model, using the standard model, we get this vacuum energy, right? That even though there's nothing, there's something there. That's dark energy. And that's because there is something there. And we get nothing in general relativity because it's based off of mass. And mass is energy to us. But dark energy is energy to mass, to matter, right? And so I think we get these kinds of, when we try and look at gravity on the quantum level, we get these singularities and these infinities because I think on some level, every single particle of mass is basically a tiny black hole because it's sucking in this energy. And since the standard model factors in this quantum energy, the quantum energy at the center of a mass should be a singularity, right? Because it's flowing into the mass. So that is where this point of, infinite density or whatever happens, because that is the concentration point of That's where it goes. That's where the energy goes. And we think that this gravity has to go on forever because we don't understand that it's just flowing into the mass. And so there's no actual necessarily singularity forming inside the mass, right? It's not that everything is actually a black hole and is, but at the same time, it is a black hole. And when we think a black hole, it is not necessarily what a black hole is. It's not necessarily a point. It is a point of infinite density, but it's not. Its strength of mass is coming from its strength of pull and its flow. Its gravity is so strong because its consumption is so powerful. And that sounds crazy because we don't see matter as live and living. And I think that's another flaw. And I know that it is so hard to believe because how could a rock be alive? And I'm not saying they're thinking hard like you and me, right? But they're doing something, right? A bacteria is taking in energy, right? And sending it back and like sending out energy, taking in and sending out energy. That came from somewhere. That evolved from something. And when you look at that from that perspective, suddenly you look at this life that is extremely it's extremely complex, but it's also not that complicated. It's basically just taking energy in and sending energy out as radiation, right? And that's all of a sudden, it's not this great mystery of where did life evolve from. It's just a building of complexity over time from what's already been there. It's no longer this great leap from not life to life. We've been building this whole time. And I know that I definitely got way off on a rant here. And I'm way off track of where I initially started. But that is basically everything in a nutshell. Light is not a wave. And mass is creating gravity through creating a flow by consuming energy and creating a gradient on which energy must flow. And it sounds like a crazy idea, or at least I think it sounds like a crazy idea. But I also think that it makes a lot of sense. And I'm not making up any crazy new formulas to make it work. I am just connecting what's already been discovered, what has been experimentally proven. But I'm proposing a different reasoning. I'm not rewriting anything technical. All the calculations are approximately the same. I'm just given a different why. And a why that is more inclusive of everything. Big and small. And I think we've been stuck for so long because we're so afraid to deny a cornerstone of what physics has been built on for the past who knows how many years. And so, I don't know. Prove me wrong. Prove me wrong. And let's see if I can't prove you wrong on your argument. Because I'm willing to be convinced otherwise, right? I'm willing to accept other claims. I just have seen too many I just see too many points where things start to fall apart. And we say, well, I mean, I don't know. I don't know. The more physics videos that I've looked at, the more I see the answer, we don't know. And so if we don't know is a common response to a lot of stuff, and all we can say is, well, we think this, then why can't we think this? And that's about all I gotta say. Peace out.